Thank you. This presentation is about a possible use of quantum computing in reliability computations. This is not actually focused on mechanical problems, since it is just a mathematical possible framework, so that it can be applied potentially to all mathematical applications. However, from the mechanical point of view, several problems are addressed from the probabilistic point of view, and in this case we start from describing some parameters like geometrical or mechanical properties of a system by means of random variables that are described by probability density functions. Then we introduce some kind of limit state function. For example, the easiest one is possibly load versus load minus strength. It must be lesser than 0. And finally, we fix some kind of outcome, and we aim to describe such an outcome by means of a final probability or by means of its probability density function as well. Actually, there are numerical methods as well as theoretical methods to do that. In general, this is a functional analysis problem, so we have theoretical results just for a limited set of applications, while in general we need to address it numerically, and probably the most widespread strategy to do that is Monte Carlo simulation, that consists in generating a large set of hypothetical occurrences of the parameters. Then we compute n times the value of the limit state function that is in general obtained by means of nonlinear analysis. Finally, we get n results, and we try to have some statistical description of it by, for example, such as the probability density function of failure of a structural response, as well as the failure probability, and so on. Actually, this is a very demanding strategy from the computational point of view, because it is very redundant, and in general if we use alternative numerical methods such as linearizations or similar, well, as long as we get less computationally burdensome strategies, usually we introduce some kind of approximation. So in general, the main problem of reliability computation consists in the computational burden. Now imagine if we just do a simple test. This is a head or tail game. We toss the coin and we wish to check how many instances of the toss are needed in order to get an appropriate accuracy of the Monte Carlo simulation. And surprisingly, if we wish to get the exact value of the outcome, that is 50%, with an accuracy of 10 to the power minus 3, we need 10 to the power 4 simulations. So actually the computational burden can be very significant for many problems of structural mechanics. The basic idea is that the very same reliability problem could be addressed in a completely different way. In particular, imagine if we can define a tool that is capable of characterizing each single random variable containing the whole probability density function of the considered parameter. then such an informatical tool can be used into some kind of arithmetic logic unit in order to get an analogous object as a final outcome of the computation that does the opposite. So it characterizes the probability density function of the limit state function so that we can get the probability of interest. Actually, since quantum computation presents some kind of aleatoric nature of the qubits description, can be quite useful. I am confident that this can be useful to achieve such a goal. Actually, qubits are informatical objects, physical objects, that are based on the properties of quanta, some kind of quanta. We have actually available different kinds of quantum transistors. In particular, the two most widespread are probably the photon, so that we have two states depending on the polarization plan of the photon, or the currents within some superconductor metals. And in general, these two are already available for scientific purposes. Simulations were focused on this kind of qubit description. In general, when we measure the state of a quantum, there are several differences with respect to the classic bit measurement, because the bit provides a deterministic binary information. So the circuit is open or closed, so it's just 0 or 1. On the contrary, while we still get a binary information from a qubit, actually this is not deterministic. Moreover, once that the measurement has been done on a qubit, we irreversibly compromise its status. And in general, the measurements present an intrinsic aleatory nature. This is the generical description of the superposition state of a qubit. I will go back on this in a while, but actually the state of a qubit is the superposition between the two basic states, 0 and 1, by means of these two coefficients, whose the sum of their squares must be equal to 1, since the squares of alpha and beta have the physical meaning of a probability to get the relevant outcome. In general, the superposition state of a qubit is represented by means of the block sphere, that is this one. It's in representation into a complex space, and alpha and beta can be transformed into phi and theta angles, describing the location of this point over the sphere. And and this is an essential point of the behavior that we wish to use for the random description. Actually, I prepared a little bit overview of the physical behavior of quanta. And this is a double-slit experiment that was basically of Young, and actually it proved the wave nature of light, because actually if we shot the light between these two double slits, then they make interference, and we can load an interference pattern on a screen. So this is a real example. In this case, we have just a single slit, and actually this is what happens with light. Since the two slits become sources of the waves, then we have these spherical waves propagating after the double slit, and they make interference with each other. And this is a phenomenon that when I was a kid I used to observe on the seaside. Okay? Now, such an experiment has been repeated also for single quanta. In general, this is an experimental outcome of an experiment performed in 2014. They used some phthalocyanine molecule, and this is again the pattern that we expect to get with light interfering between the two slices. And what happens is that once that the quantum is shot along the two slices, then there is again some kind of interference after the first screen here. Now, when I started to get involved with quantum computers, I imagined electrons and quanta in general as single pallets that had some kind of associated wave propagation. So in general, the fact that the quantum state was undetermined was not, from my point of view, was not an intrinsic uncertainty, but was a lack of acknowledgement by myself. On the contrary, this experiment proves that since we shot just a single quantum through the two slices, then the single quantum makes interference with itself, so it passes through both the slices. And as I said before, when we make measurements, meaning that we interact with quanta, then we irreversibly adulterate their state. And in general, this can be observed if we set a measurement system just before the two slices. Because when we perform a first measure here and the second measure here, we lack the interference pattern. This means that quanta present a coupled double nature. They are waves in general, but when something interacts with them, even for doing measurements, then there is the phenomenon of decoherence of the wave, so that the particle collapses in a single point. And that's why here there is the first collapse, and then there is no interference anymore after the double slice. This is essential because it means that in general the superposition state does not mean that quantum transistors have a deterministic state and we don't know the state measure. But, and in this case it would be an epistemic randomness, a lack of acknowledgement by the observer. On the contrary, superposition means that quantum transistors are in different states, a superposition of different states at the same time. So their nature is intrinsically random, and the description comes out to be aleatoric more than epistemic. So there is an intrinsic randomness of the phenomenon. This is an essential point in order to provide some reliability tool. And in general, as I said, after that measurement is done, the outcome goes back to a deterministic state. So it is just 1 or 0. In general, an important property of qubits is that when quanta interact with quantum gates between themselves, then the whole coherent wave amplitude is involved. So there is no collapse until I get a measure. So if I do computations by some quantum circuit, then there is the whole information that is transmitted by the quantum transistors. in this case, quantum computation can be considered as a sort of intrinsic parallel computation, and this is very common interpretation of it in the current state of the art. However, when measures are performed, the quantum computer provides us the probability to get 0 or 1, so it already provides some probabilistic information. Hence, if we have a parallel computation and a probabilistic description of the outcome, from my point of view, quantum circuits can be seen as intrinsic tools that already perform a sort of Monte Carlo computation, because we have a lot of informations within the superposition state and we get a probabilistic outcome of the measures. So, the idea is that because of such parallel nature, we don't need anymore a train of different simulations with an equal number of outcomes and then statistical interpretation of them. But we can use randomness, the randomness of qubits, to make them to interact in order to describe random variables. A second point, important point, is that from the computational point of view, when we perform Monte Carlo simulation on classical computer, these are not really random. These are pseudo-random generated numbers. On the contrary, randomness of quanta is real. It is not simulated and it is not affected by parasite phenomena such as the classical computer. So, in this sense, my idea is to provide a framework to perform a direct approach to random computation, just to make computations on the limit state function. And in general, if we go back to the previous slide, the idea is that if I have a set of random variables, I can initialize the superposition state of many qubits in order to be consistent with the probability density function of the variables. And so we have two superposition states. These can be interpreted into an arithmetic logic unit, and then we get a final superposition state relevant to the limit state function, so that if I am able to make the backward interpretation of this superposition state, I can get the probability density function of the outcome. And actually, the research that I am presenting is focused on these forward and backward operations with random variables. I used a string of n qubits in order to provide the classical binary description of numbers by powers of 2. And I used different probability mass functions in order to investigate different behaviors, and I made superposition of such quantum states through quantum gates. So in general, we have this string, and the final integer number is equal to this sum here, where q0, q1, and so on are the states of each qubit, and then there are power of 2. Then, if we consider a probability mass function, that is just the probability density function relevant to a discrete random variable, then I can compute the marginal probability relevant to each one of these qubits. This is the determination that every single qubit is equal to 0 or 1 consistently with this function here. And this can be done in closed form because just a couple of summations. In general, it's quite a linear combination of known quantities. So I can initialize, when I compute these probabilities of each single qubit, I can initialize the superposition states so that beta square is equal to the probability that the single qubit is equal to 1. And obviously alpha is the probability that this is equal to 0. The backward computation is just a product by using the classical total probability rule. So the probability of relevant to number x is equal to the product of all the probabilities of each single qubit. So here I have the outcome that is equal to 0 or 1. If this is 0, then I make the product with alpha. On the contrary, if this is 1, then I multiply this quantity here, that is beta. And in general, this is very fast operation, both forward and backward. So, let's see at some involved quantum gates that are used for initializing and adulterating the superposition states of qubit. This is a generic rotational gate. This is a rotation about the y-axis, and this is generic rotation, but we will use the just rotation along y. And in general, all quantum gates are represented by linear combinations of the wave amplitudes. And moreover, I will use 3 more gates. The first one is the NOT gate that is analogous to the classical binary one. It just switches the states of a qubit. If it is 1, it switches to 0 and opposite. Then the C0, the conditioned NOT. So if the state of this first qubit A is 1, then the NOT gate on a second qubit activates. And the 3-qubit Toffoli gate, that is a double conditioned NOT, so if the qubit A and B are equal to 1, then the NOT gate on the third one is activated. And these are represented by these simple matrices involving the tensorial product of the qubit states. So, in general, when we apply a rotation about the y-axis, then if the initial qubit state is 1, 0, this is alpha and this is beta, so actually it is a deterministic information equal to 0, analogous to the classical computation here, I can compute the beta probability by the expression that I have shown before, and then I compute the theta angle that must be introduced in the gate in order to get a new superposition state that is consistent with the probability distribution of the variable. And these are 2 applications. The first one is the discrete geometric probability mass function, and while the blue line is the theoretical, the red line is the outcome of the quantum computation. And this one is a constant distribution up to 15 or 14, I don't remember. Anyway, even in this case, we have a perfect incidence of the outcomes. So, such results are pretty encouraging. At least they tell us that such a strategy can be actually used for random variable description. However, if we use different distribution, then things are more complex, because in that case, when I computed the marginal distributions of the qubits, then the red line is what we get. And actually this is completely incorrect. The reason is that actually there is a statistical dependency between the states of the qubit, some sort of correlation of their states. In fact, if I consider just a generic, this is just a picture, but let's imagine that this is...
Are you calculating your time?
How long?
I think that you have a few more minutes.
Few more minutes, okay, I will speed. Okay, if we have such a probability density function and we set that the last qubit is equal to 1, then this is the probability relevant to the last qubit, but when we go to the n-2 qubit, then the probability that this is 1 is the area, the blue area underneath the curve. On the contrary, if the last qubit is equal to 0, so it belongs to the left area, then the probability relevant to this qubit is the area in green. So in general, the probability of each qubit depends on the states of the higher qubits in the string. And in general, they're not independent. So we need to modify the superposition state accordingly. In this case, this is a 2-qubit example. So we have the initial state here, and then we have a conditional rotational gate. So if this is equal to 1, then I make a rotation in order to set the probability to this area in blue. This can be repeated. I was too fast. Okay, these are some analytical details. This can be repeated even for more qubits. This is an example with 3 qubits. In general, we have more conditions, and we should address different combinations of them, but in general, we just need these gates here, and most important, one additional qubit, this the ancilla, it must ensure that the operation is reversible. And also, I did it with 4-qubit description in here, so in this case we have a lot of more gates. I can go into details, but we have just 2 ancillas and in general about 50 gates. Actually, such a circuit enforces the correlation between the qubits, and I'm almost done, because in this case, with 4 significant qubits, this is the description of the binomial and discrete beta probability density function, where the red one uses the marginal probabilities of the first case, while the yellow line is the outcome of the circuit that I have shown in the previous slide. So in conclusion, I think that such results are encouraging because we can actually use quantum circuits to describe random variables. Superposition states can be determined in closed form for a given probability mass function. And after qubit measurement, we can do the opposite, so we determine the probability density function of an outcome, again in closed form. In general, we have correlation between qubits, so we need a circuit entrusting it, and when correlation is taken into account, again we get a perfect match between the theoretical and the computational density functions. We still have some open issues, since we are working on suitable arithmetic logical units that must be properly designed for this application, and as well as description of negative and floating point numbers, and extension to larger sets of qubits with a limited use of ancillas. And I hope to be in time, so I thank you for your attention, and I really are open for suggestions and feedbacks from you. Thank you.